All right, here's an exam style question that makes us think about ion pairing. So to remind ourselves, why do we care about ion pairing? This is in chapter 15, 13.5. So on colligative properties. And remember, these are the properties that we say, hey, we don't have to consider how the solute and solvent actually interact. We just need to know how many particles of solute have been added to our solvent, and that's going to dictate the change. And so when we go, in this case, this is a boiling point question. Okay, so boiling point elevation was one of our colligative properties, and we said that delta TB equals I M KB. Let's remind ourselves what those are. KB is the molal boiling point elevation constant. So I'm just going to write instead of that mouthful that it's a constant and depends on solvent. Okay, so like KB in this case, since it's an aqueous solution, KB is just reflective, is just whatever it is for water. Okay, it's like, and it's just always, if it's an aqueous solution, we will always use the KB for water. Okay, M is the molality. And remember, molality is moles solute per kilogram solvent. All right, so there's our connection between the boiling point change and the number of particles, right? So if you have a really high molality, you're adding a lot more solute. So that means that you should have a larger change in boiling point. And then of course, we got to the Van Hoff factor, okay? And this was really important when we considered ionic compounds because ionic compounds are electrolytes. So when NaCl, so right now it's solid. I'm going to put it into some water and it becomes aqueous. It dissolves. I wind up with Na plus aqueous and Cl minus aqueous. So when we said, hey, colligative properties depend on the number of particles, when I put 1 mole of NaCl into solution, I'm actually getting 2 moles of particles because every time I put this in, I'm getting an Na plus and a Cl minus. So this translates to 2 moles of particles, right? So we need to have that represented in our delta TB expression, and we do. That's the I. That's what the Van Hoff factor brings in. Hey, NaCl breaks up when it goes into solution. We care about the number of new particles that we've added, and this adds 2. All right, so that's true actually for both of our solutions in this question, right? So a 0.2 molal aqueous solution of NaCl, and we're comparing that boiling point to a 0.2 molal aqueous solution of magnesium sulfate, okay? And so again, we want to know like, well, magnesium sulfate, and you have to remember here that sulfate is one of our polyatomic ions. So when this dissolves in water, we're going to have Mg2 plus aqueous and SO4 2 minus aqueous. So we have to remember that this thing travels as a unit. That travels as a pack. And so if you're struggling and you don't remember that, go back and review polyatomics. Polyatomic ions. All right, so you have to, part of this question is you have to look at this and say, I know that Mg2 plus and SO4 2 minus are going to be my component ions, so my cation and my anion. All right, so in this case too, if I had 1 mole of magnesium sulfate and I put it into solution, I would get 2 moles of particles. All right, and how I've been discussing this so far is with the expected I value. All right, and so that's where this twist comes. So if I were just going to assume ideality, like that all of these particles are going to split up, then I would expect these two to have the same boiling point. So without ion pairing, all right, let's be more clear. Without considering ion pairing, these two solutions would have the same boiling point. right? Because both have an I of 2. They both split up into 2 particles, so the Van Hoff factor is the same. In this question, we see that both of them are 0.2 molal solutions, so M would be the same. They're both in aqueous solutions, which means the solvent is water, so Kb would be the same. Okay, so if I didn't consider ion pairing, I would say that they have the same boiling point, and that would be the end of the story. However, in this question, we see that we're not going to make that assumption. We're not assuming the expected I value. So in class, we talked about this as I expected. Okay, I expected for NaCl and magnesium sulfate, both are 2. So I expected equals 2 for both of them, all right? However, when we actually go to make these solutions, we see that delta TB is not the same for these 2, and that's because of ion pairing, all right? So let's remind ourselves what ion pairing is. I bet you didn't think I could give you this long of an answer for this short of a question. All right, ion pairing. When we do put these salts into solution, and remember for colligative properties, it's about the entire, like how many new particles are in there. Occasionally, Na plus and Cl minus will come together in solution and be NaCl, okay? Like a unit like this. That's an ion pair. All right, so for that moment, and they don't stick there forever, they come together and then they come apart, and then they come together. So it's an equilibrium. But at any given point in a solution, some of this is going to be happening. So where initially when I said our I expected is going to be 2, because we're doubling the number of particles, now that 2 is an overestimation, because some of these Na pluses and Cl minuses are actually coming together to be 1 particle. Okay, so we have to consider this ion pairing contribution. Okay, and the key in this question is to compare the ion pairing between NaCl and MgSO4. Okay, all right, let's do that then. Which will ion pair more? All right, so we've already drawn this out. And they're at the same concentrations. If they were at different concentrations, this would be an unfair question, because concentration is one of the things that dictates how much our ions actually come together in solution to make that ion pair. So you'll see this question and we'll either control the concentration like we did in this one, or we would control the salt. So I'd compare like a 0.2 molal solution to a 0.4 molal solution, but both of NaCl. So I have to isolate the variable, otherwise it becomes too challenging of a question. I think I could probably figure it out. Anyways, that's a side note. You're like, please just get to the answer. Mg2 plus, all right, we're gonna compare Mg2 plus to SO4 2 minus. I expected is 2, but we are thinking about how regularly will these 2 come back into solution, come back together to make this ion pair. And that is going to happen more regularly with magnesium 2 plus and SO4 2 minus because of these charges. Their electrostatic attraction to each other is bigger because their charges are bigger. So MgSO4 ion pairs more than NaCl because of the charges. All right, so I would expect in the same solution, in the same concentration that I measured for MgSO4 is going to be less than the I measured for NaCl, because these ions are going to come back together a lot more. They have a larger charge, they're more attracted to each other. So I'm going to have more ion pairs, which means fewer particles in the solution, which means I should be multiplying here by a smaller number. All right, so I think we've covered all the things we need to now answer this question. All right, so a 0.2 molal aqueous solution of NaCl will have a greater or higher, I don't remember, a higher boiling point than 0.2 molal aqueous solution of magnesium sulfate, because NaCl will ion pair less than magnesium sulfate. And then the underlying thing here is that I of NaCl is going to be greater than I of magnesium sulfate, and that's because of the ion pairing. So again, a single sentence, and I can explain it, take 10 minutes to explain it, but hopefully you got something out of that one.